Okay, so here's where we were last time. We were talking about the arc length parameter. The lead-in idea is this idea of reparametrizing a curve. So here we have a curve, here we have a parameterization. Here's another parameterization, right? And I suppose you can think of this as just an independent thing, but I'm pushing this idea that you can think of this as coming from this kind of change of variables, as it were. So in particular, everywhere I see a t, I put q cubed plus q, and sure enough, that gives us exactly this other parameterization. So whenever you find yourself with a relationship between potential parameters, and there is a little sticky wicket on this. This relationship does have to be invertible. Let's not get lost in the weeds here. You can just kind of plug that in, and you have yourselves a new parameterization. So the specific application of this that we ended with was using arc length, right? And the big idea is that if you have position as a function of time, okay, well, yeah, but distance is a function of position. Is a function of time also. So there's this algebraic relationship between time, our original parameter, and position, distance traveled, our new parameter. And you can just plug that in, and you get a new parameterization called the arc length parameterization. Position as a function of distance. So again, now my personal favorite metaphor for this is, when you're driving along the interstate, they have mile markers. That's literally what we're talking about here, right? So those positions where those mile markers are planted and denoted with respect to how far those positions are away from some designated starting point, which I actually don't know how that works in the actual real life. It might vary from state to state. I don't know. It doesn't really matter, right? But the point is that's what an arc length parameterization is. So I think that's where we left off last time. I will point out that there's some nice things about the arc length parameterization. First of all, kind of a philosophical point, it's intrinsic to the curve. How long it's going to take you to drive from Durham to Charlotte? I don't know how fast you drive. I don't know. This is about you, right? That's individual. But how many miles is it? And where will you be after you've traveled 48 miles? That's got nothing to do with you. Doesn't matter how fast you drive. Doesn't matter if you are driving at a constant speed, or if you're accelerating and decelerating a lot. It doesn't matter. Position as a function of distance is intrinsic to the curve itself. So that's got its merits. I also think it's a nice little clever observation to look at the single variable chain rule as it applies to this little quick change of variables. So position as a function of time, position as a function of distance. Well, distance as a function of time, you could just literally write down the single variable chain rule, and notice, taking the magnitude of both sides, this is the magnitude of the velocity, aka your speed. This is distance per unit time, aka your speed. So these two expressions are equal, and that means that this is 1. And in particular, that means that if you forget about time, if you look only at position as a function of arc length, right? In other words, if you use the arc length parameterization, the velocity of that arc length parameterization always 1. And this has some really nice convenience that comes up in various contexts. The bad news is this is all kind of an abstraction because it's very hard. Even in the most, there are a few extremely narrow circumstances in which it's computationally feasible. But most of the time, generically, it's just not. And here is a scenario where I've gone to some trouble to try to make this as convenient as possible, believe it or not, without being trivial, right? This parametric curve, let's just kind of walk our way through it. Here's the formula for arc length. Right? And you can kind of multiply this all out, take the appropriate derivatives, take the magnitude, blah, blah. What you'll notice is that even though we get scared when we see this square root here that comes from this magnitude right here. And there's the potential for the algebra here to become horrifying, right? I went to some trouble to carefully arrange things to where, in fact, it's a square root of a perfect square, and the square root goes away. Isn't that nice? This is about as good a news as we could expect, other than trivial cases. About as nice as we could expect it to be, and yet, still, notice, I'd have to solve for t. If I wanted to plug this in to this original parameterization up here, I would need to solve for t. I can't solve for t. It's a cubic, right? So even in the kind of extremely lucky, fortunate cases, it's still hard to compute. So this is more of an abstraction than a practical thing, and that's why I don't want to spend much time on it. But I do think it's important that you know what it is and why it's interesting. Okay, moving along. A new kind of object. We're going to talk about vector fields. It turns out this is really, really, really important. This is going to be our primary object of study in chapters 6 and 7. The sections, the chapters that the engineering school has explicitly told us these are the most important ones, make sure the students are really good at that stuff, is going to be all about vector fields. So really important to know what they are. Here's the definition. A vector field on Rn is a function from Rn into itself. So specifically, the dimensions here have to be the same. Rn to itself. Okay, now the tricky little thing, in order to view this as a vector field, we are further going to think of it a certain way. Let me make a different color choice here. The point in the domain that goes in, we're going to view that as being a point in Rn. The thing that comes out, we're not going to view as a point. We're going to view that output as being a vector. So even though they're both elements of Rn, the input we think of as a point, the output we think of as a vector. And then I can draw the following picture for every point in R2, for every point in R3. For example, if I have a vector field in R2 or a vector field in R3, for every point, there is a corresponding associated, what we call field vector, which we represent by an arrow with its tail at the given point. This is just how you draw vector fields. For every point, there's a corresponding vector. Now, you'll notice that this picture that we've drawn, it's not a graph. It's not a level set. It's not an image. What is this, right? We've got these very different kinds of pictures that we've drawn to now. This is none of them. This is its own, I guess you could say, our fourth different kind of picture that helps us understand a function. Yeah, sure, to be fair, this is a function, and this is a picture we're using to understand it. Completely different from any kind of picture we've seen before. Now, let me remind you the reason that's important. When we were talking about graphs and level sets and parameterizations and stuff like that, the big idea was you can't know how to interpret a picture if you don't know what kind of picture it is. Right? There's a calculus of graphs where certain geometric features tell you certain things about the calculus. But then there's a completely different calculus of level sets, where different geometric things are interpreted as different bits of calculus, right? So totally different kinds of calculus. There is going to be a calculus of vector fields, and it's going to take us a while to actually flesh all of that out. That's arguably the subject of chapters 6 and 7. To try to figure out what calculus looks like and what does it look like, what does it mean, and how do we interpret it. So that'll take a while. Okay, all of that said, let's see some examples, try to get a feel for what vector fields look like. Here's a couple of them. This first example is a nice, easy little starting example. Notice for every point, for every point in space there, our field vector is always 2, 1. Again, represented in each case by an arrow with its tail at that given point. So this is what this vector field looks like. You'll notice this is a constant vector field, right? The right-hand side, the value of this function never changes. It's always 2, 1. So this is what a constant vector field looks like. Now notice, it's not like a graph, right? If it were a graph, then it would be like horizontal or something, right? Not so with this kind of picture. So again, make sure to consciously separate in your mind geometric interpretations in the context of graphs versus in every other context, and in this case, vector fields. How are we doing so far? Is everybody with me? All right, next example. Another sort of interesting, I don't want to say simple, but starter example. Here, the point x, y. Okay, there it is. There's that point, x, y. Before I get to interpreting the field, I will point out, check it out, the output's the same as the input. That's pretty glaring, right? How are we going to take advantage of that? But further keep in mind that the output has to be viewed as a vector. So if I want to say they're the same, I need to first reinterpret the input as a vector in addition to being a point. So how do I interpret this point as a vector? Well, we use the position vector, right? So that position vector is what my field vector is. That is my field vector. I just have to draw it as we're supposed to with its tail at the origin, its tail at the point in question. Right. So there you go. Everybody on board? Now I'm going to leave it as a little bit of an exercise for y'all to take this example of how this vector field looks at that point and analogously think it through for all these other points. And I claim that overall, this vector field looks kind of like that. It's a bunch of field vectors all emanating outward away from the origin. Something to think about. Okay. All right, next example, and this one is a little bit more work. Let's see here, I'll do it like this. Actually, I'll do, there we go. So, yeah, here, no such luck at our point x, y. Let's think about that point right there. The field vector is not constant. It's not the same as the input. And what am I going to do about this? In general, wow, how am I supposed to just write down the picture? I guess I could go point by point, right? But a pretty neat observation in this case, the input point, thought of as a vector, the output vector, those two have the same magnitude. Kind of notice that? You'll also notice that they are orthogonal. And so both thought of as being vectors, they are perpendicular. So that means that at this point, with that position vector, my field vector here has the same magnitude and is perpendicular. And that cuts down my many options to either that or that. These two that I have drawn here are the only two vectors that have the same magnitude but are orthogonal. So which one is it? Well, I'm going to flash y'all back to linear algebra, and I claim that this vector field can be thought of as a quarter-turn counterclockwise linear transformation. What I'm going to encourage y'all to do is to write down the matrix representing a quarter-turn counterclockwise linear transformation in R2. Make sure you know how to do that. And then when you apply that to x, y, what you'll find is you get negative y, x. So make sure to work that out. And that being noted, the punchline then is that this is the field vector. Yeah?
Is there a certain unit where the rotations were covered?
Is there what now?
Where the rotations were covered, like modeling the rotations as a matrix?
You said a unit, as in like in the book. Yeah, well, kinda. I mean, so I said a few quick words about it in like on page 2 or 3 of the chapter 1 notes. That was in section 1.6, and they didn't talk specifically about geometric linear transformations like rotations and reflections and stuff. But I don't think I did any explicit examples. But the big idea is that if you want to represent a linear transformation with a matrix, the columns are the images of the standard basis vectors. That's the big idea. And so just think in terms of what happens to the standard basis vectors when you do a quarter turn counterclockwise, and that'll give you the matrix. Yeah, sure. Okay, so vector fields, it's a different kind of picture. Takes a little getting used to. This is what we're talking about. Okay. All right, next example. This one's really useful in physics. This vector field right here. This is a very compact way to represent it. It's not a very good way to think about it. So you'll notice I've rewritten it like so. And in this point of view, this being my vector field, notice the field vector is always a unit vector. Furthermore, keeping in mind that x represents position, and that's just a unit vector pointing in the same direction as the position vector, that's always pointing radially outward. It's always a unit vector. Oh, that's bad art. There we go. It's always a unit vector pointing exactly away from the origin. And then there's a magnitude here. Scalar in front of a unit vector is the magnitude. And notice that that's inverse square. So because of this radial outward unit vector and this inverse square magnitude, we call this a radial inverse square vector field. And it's worth giving this a name because it comes up so much. In fact, this is exactly the formula for a gravitational field, for an appropriate choice of C. It's also exactly the form for an electric field created by a single point charged particle. So these kind of a big deal, right? I mean, these are some of the most important vector fields involving forces. Gravity and electricity. Right? So all intrinsically represented by a vector field and conveniently represented by the same one. Now here's just a little personal note, a little bit of advice. If y'all are, some of y'all might be engineers or physicists. I found it extremely helpful when I was trying to get a sense for what do electric fields look like and how should I think about them. Just think about gravitational fields. Structurally, they're basically the same. So whatever sense of understanding and intuition you have for gravitational fields, good news. You also have, you might not have realized it yet, but you have that same intuition for electric fields also. Really nice fact. Big payoff for me anyway. Okay, how we doing? Everybody all right? Okay, gradients. We've talked about gradients before. If you have a function like this, here's the gradient. Easy calculation. What's new? What's new here is just an observation about how to think about this, right? And if you look back at what we've done with gradients in the past, we've only ever looked at the gradient one point at a time. Right? For any given single point, that one point, we talked about the gradient vector at that point, and only that point, just myopically sort of focused, narrow tunnel vision on just what's happening at that one point. And the observation we're making now is, no, it's a vector field. Even though, you can focus your attention one point at a time, it remains that this formula right here gives you, for every point in the domain, right, for every point in the entire xy plane, You plug in the x, you plug in the y, and there's a corresponding gradient vector, aka field vector, at that point. Right, so if you take this old observation that we'd made about how on a graph, such as this paraboloid right here, this is the graph of that function, x squared plus y squared. If you're looking at a graph, we already knew that the gradient always points uphill. What we see here is that the gradient field, the entire vector field, all at the same time, all of those vectors all point uphill on the graph all at the same time. Not really a new statement, just a new way of thinking about it. Is that cool? All right, now there's a little bit of a frustrating bit of terminology here I need to talk about. I'm going to start off with the way I kind of feel like it ought to be. It's one of the perks of being the instructor. To me, when you're talking about taking a gradient, it seems natural to me that the thing that comes out should be called the gradient of, I think this is pretty uncontroversial, right? That's what it is. It's the gradient of what went in. Okay, now let's talk, though, about what to call the other thing, the thing that went in the first place to produce a given output. If I have a vector field and I want that to be the gradient of something, what is that something called? In other words, given a vector field going backwards through the gradient operator, what should I call this thing? And I think this is a pretty hard to argue with choice right here. It's the anti-gradient. Think about the terms derivative and antiderivative. Right? The thing you take the derivative of to get a given output is the antiderivative. Well, likewise, let's call this the anti-gradient. Very natural to me. All right. Now, let me talk about what the more common terminology. Physicists like to point out that there is a reality that relates gradients to potential energy and forces. And loosely speaking, potential energy, let me just use gravity as a nice example. If you're talking about how gravity works, gravity has forces. There is a gravitational force. There's also this idea of gravitational potential energy. The gradient of potential energy, being a gradient, it always points in the direction of increase. That's up, right? Potential energy increases as you go up. The force, though, points down. That's just how the physical world works, right? So force is not the gradient of potential energy; it's the negative of the gradient of potential energy. And you can gravity is the most easily relatable example of this, but this works in any kind of a potential situation. So with that in mind, being that the anti-gradient relates to potential energy, very often this function is called a potential function. And frankly, this is the more common term. And I see the motivation, right? Sure. I have two quibbles. My biggest quibble is, what about that minus sign? Right? I mean, in some sense, potential energy is the exact negative of what the potential function is. So I think that's really awkward. I think that's it's easy to mess this up and then to kind of lose minus signs because, if you think of potential function as just being potential energy, well, then you're wrong by a minus sign. And the language kind of talks you into it. The language conceals that minus sign. I think that's a problem. So that's why I like the term anti-gradient better. This problem disappears. So it's my personal preference. The other reason that I'm not super big on this terminology right here is that this makes sense in physics, and we're not always doing physics. Sometimes people are doing economics, right? In which case, Who cares about a physics metaphor? It's got nothing to do with what we might be doing. So anyway, again, terminology is not up to me. You're going to hear me say antigradient. You're going to hear outside of this class people say potential function. Okay, how are we doing on this? Any questions? Is everybody happy? Okay. All righty, moving along. Okay, so we've seen a couple of examples of forces that can be represented by vector fields. Here's a totally different physical metaphor for vector fields, and that's the flow of a fluid. And there's a ton of examples of fluid flows. Three-dimensional fluid flows, after all, we do live in 3 dimensions. The way air is flowing around in this room is a flow of a fluid. Air is a kind of a fluid in a way. It's not a liquid, it's a fluid, right? And so, for example, at any given point, like right here in space, I can talk about what direction and with what speed is the air flowing at that point. And there's an associated vector. So at every point, there's an associated vector. It's a vector field. So a vector field is a way to represent how air is flowing in this room, or how water is flowing over the ocean, how pollution moves through a lake or a river, how ozone is flowing around in the atmosphere, what have you. Okay, easy examples there. Now, there are also some 2-dimensional examples. And I'll point out that even though, yes, we live in a 3-dimensional world, we kind of live in a 2-dimensional surface of a planet, right? So a lot of what we do in this world is intrinsically 2-dimensional. So the easiest one to talk about, I think, is surface water. How does water flow around after rain? And it's in various little rivulets and creeks and streams and stuff. And how does that water flow? Well, it flows downhill, and that means that on a map, at any given point, you can draw an arrow representing which direction and how fast is the water flowing at that point on the map. That is a 2-dimensional vector field representing surface water. And I'll also point out this one I think is kind of fun. Animal migrations can be thought of as a vector field. Now, I like the idea of a huge herd of some let's say wildebeests, whatever, it doesn't matter. Thousands and thousands of wildebeests, and as they kind of go along, well, they're all kind of going with each other in some sense. At any given place in there, they're all kind of going the same speed, same direction, same velocity. So the movement is represented by a vector, and again, you could represent that with a vector field. And complaint could be levied that that's not a fluid. Right? It's a bunch of animals. The animals aren't a fluid. If you think about it, what is water? It's a bunch of little particles called molecules. So you know what? Really, all fluids are really a bunch of particles that are all kind of somewhat moving together. And yes, there are finer particles in water and air, and there are coarser particles in a herd of wildebeests. But it's not really all that different. So, I'm done. I'm to chew on. Yeah?
If we had like a vector field in like R4 or above this, is that even possible?
Oh, sure. Yeah, I can't visualize it.
Okay, so you
Yeah.
can't like visualize.
Yeah, oh yeah. No, nobody can visualize above 3 dimensions. So, let me rephrase that. I don't believe anyone who claims that they can visualize above 3 dimensions.
Is there a way we can like minimize it or like have another interpretation?
Yeah, there's some neat games that you can play. It's not something that I can in good conscience spend class time on, but there's some little workarounds and hacks to help in certain ways with that. And if you want to talk about that sometime, just come talk to me. Yeah. But it's nothing that anyone needs to worry about in this class. We're going to, as far as vector fields are concerned, we're going to stick with 2 and 3 dimensions. Yeah. Okay. Now, let's do a calculation. Before I get into the nitty-gritty of this calculation, I want to talk about what's going on here. We're going to start assuming we have a vector field that represents velocity of a fluid. And I'll point out that's pretty natural, right? Let's think about the air in this room. Again, at a given point, right there, I mean, there's airflow. I hear the air is on somewhere in here. At that point, the air is moving with some velocity. So at every point, there's a vector, boom, vector field. The units here for velocity would be something like meters per second, right? Inches per minute, what distance per unit time. All right, now here's a related question, very much not the same. Suppose you have some small flat area, like this. Okay, now there's air that's flowing around, like so. And I appeal to your geometric intuition. As the air flows like that, a certain amount of that air is going to flow through this surface. Let's imagine this surface is like a screen or something where there's a well-defined surface, but the air can pass through it, right? So a certain amount of air will pass through that surface in a given amount of time. And that gives rise to something called a flow rate. Not to be confused with velocity. Now you see the word flow rate and you're thinking, okay, well, all right, flow, that, yes, sure, the fluid's moving. You see rate and you think speed. But that's not what flow rate is. Flow rate is not distance per unit time. Flow rate is volume per unit time. Does that make sense? So again, if we have a screen here, there's a certain amount of volume of air per unit time that passes through that surface. Everybody see the distinction here between the velocity and the flow rate? So the question is, how do you compute the flow rate from the velocity? And that's going to be a whole thing here. So let's dive into the details. And let's see here. We are basically going to be computing the amount of volume that passes through our surface in some amount of time, delta t, right? So if I can compute that amount of volume, and then I'll divide by delta t, and that'll give us the flow rate. So let's start with the volume. How do I compute that volume? The volume is this height. Let's see here, times this area. Right, height times area gives me volume. The height, let's see here, this is going to get messy. The height there relates to this, what I'm going to call displacement vector. Let's talk about this displacement vector. Keep in mind the fluid is actually flowing with a given velocity for a given amount of time. And if you know the velocity and you know how much time you're talking about, then velocity times time gives you displacement, right? And conveniently looking at this picture, this height and that displacement relate by way of this normal vector, right? If I look at the unit vector perpendicular to the surface, this height is the normal component. Let's see here, color coding. The normal component of that displacement. Everybody with me? Okay. All right, and it's kind of all over with the shouting at this point. Let's see here, yeah, so the normal component, that's a component in the direction of a unit vector. That means it's a dot product. Let's see here, the displacement vector here, that displacement vector is velocity times time. Don't forget, of course, that the vector field is the velocity. So this just says velocity times time is your displacement. And there's our delta V, and we divide by delta T, and altogether our flow rate is this part, and that's what we call flux. So given a vector field and a piece of surface, we can talk about how much volume per unit time of fluid is passing through it. That's called flux. It's computed with this formula. Yes?
I'm just trying to visualize it. Where's like the fluid? Which way is the fluid?
Yeah, so the fluid is doing what the vector field is saying, right? So as it says up here, the f of x represents the velocity of the fluid. So the fluid is like this, and you've got this surface that's kind of angled down here and kind of like this, and then a certain amount of that fluid is going to be actually passing through the surface.
It's like a hole. It's going through a hole.
Yeah. Imagine it's like a screen, and that you can pass right through it. Yeah. Another metaphor I like is if you have a net in the ocean, and the ocean current is taking water. It's not blocking the water, right? The water goes right through it, but water going through the net is how you're going to catch fish. Does that make sense? Yeah. Good. Everybody else all right? Okay, so yeah, really big deal. It turns out that flux is useful for many things other than catching fish, right? And we're going to see a lot of those applications later on when we get into chapter 7 mostly. But this thing called flux can end up being a really big deal. Okay. Now, here is a related question. An exercise, another one of these, on your own time, at your leisure, suggested exercises. Reminded that when the vector field represents velocity, flux represents volume per unit time. I claim that if you were to just use the vector field in a slightly different way, if you were to let the vector field represent density times velocity, you would get mass per unit time instead of volume per unit time. So the way you're going to show this is almost exactly the same as this right here. There's just going to be an extra factor of density thrown in that will then factor back into the vector field at the bottom. That all works out. But it's a lovely little exercise. It's a great way to confirm that you really understand the ideas going on underneath this calculation, is if you can adapt it appropriately to this slightly different circumstance. So give that a try. If you get stuck on it, as always, please come to my office hours. I'll be very happy to talk you through it, give you whatever hints, or just show you how to do it, whatever is needed. But like I say, I think this is a healthy exercise. All right. Okay, let's see here. Moving along. Oh, I'm sorry. One other thing I wanted to point out about this. So we talked about this unit vector here in as representing that's the direction perpendicular to the surface. And of course, so we have this surface sitting here like this. And the in vector is a unit vector perpendicular. It's kind of a way of describing how that piece of surface is oriented in space, right? So you can, if my surface is like my hand here, my stylus there being perpendicular to it is telling me how the surface is oriented. Right? If the normal vector is different, unavoidably the surface is sitting in space in a different way. Is what we call an orientation. Okay. Here's the thing. That surface, exactly as it is also perpendicular to that vector. There are two perpendicular vectors, perpendicular unit vectors that I could have used. Which one's right? And the answer is it depends. It depends on your scenario. What this normal vector does is it simply designates what is to be considered the positive direction through the surface. So in particular, if my fluid is like this, and it's flowing through, in that direction as we were considering, what am I going to get for my flux? Well, it's going to involve this F dot this N. You can see that dot product is positive because the angle's an acute angle, right? This would give us a positive flux, meaning that this direction that the normal vector is pointing, that's what we consider the positive direction through the surface. Okay. Now, what if I were to have my normal vector be like this? Well, then I claim that would be designating this downward direction as being the positive direction through the surface. Now, why is downward, wouldn't upward make more sense to be positive? I don't know, it depends. Not in basketball, right? In basketball, the ball's got to go downward through the hoop, right? Sometimes it makes sense to think of downward as the natural or the positive direction. Whatever the circumstance, if that's the case, and this is the positive direction, this exact same vector field, flow still going in that direction, well, if this is the positive direction, then this is going opposite of that. This would be going in the negative direction through the surface, as suggested by this choice of normal vector. Would that show up in the calculation? Why, yes, it would. F dot n, looking at these two vectors here, F dot n would be negative, as it should be. So you get to decide for yourself is ultimately the answer to the question, which direction is the positive direction through the surface? It depends on the scenario. And your choice of which of these normal vectors to pick should be informed by whatever your circumstance is and whatever makes the most sense in that circumstance. So, something to think about. All right. We'll get a lot of practice, by the way, thinking about there are some situations where there really, really is an importantly natural right answer for which normal vector to pick. And we're going to see those examples in Chapter 7. Okay. All right. Okay, moving along. If I can get this thing to come on. There we go. Okay. This next page, I'm going to be real quick about this. This is pretty supplemental. We are behind schedule, as I'm sure you all have noticed. For the record, since we're on that topic, I'm always behind schedule. I always catch up in the end. It's fine. I front load the schedule because there's so many tough choices to be made. There's so much that I just don't have time for. I need to constantly be reminded that I'm in a hurry and that we have to make those tough choices. So anyway, we'll be fine, no problem. But sadly, I'm just not going to have time to talk about much of this. I just want to point out what this is fundamentally about. So I want to point out that sometimes the fluid doesn't really have a very well-defined velocity. Let's think about a scenario where we have two light bulbs, right? So there's one light bulb that's spitting out photons, which again are little teeny tiny little particles that flow along and thus make up a fluid. A little bit weird to think of light as a fluid. Kind of is. And then here's another one. I've got another light bulb right there, and it's spitting out photons and making a fluid analogously. And now let's think about what's happening at this point over here. What's the velocity of the photons at that point? And short answer is I don't even really know how to answer that question because some of the photons are going like that from that green light bulb, and some of the photons are going like that from that orange light bulb. It's not. Neither one of these is the right answer. I mean, at this location, there's photons going both different directions. So neither one's right. Everybody see the problem? Water doesn't do this. If you go anywhere into the ocean, however deep in whatever longitude, latitude, wherever whenever you're looking at any given point, the water is going one direction at that spot. Not so with this weird fluid of photons. They just pass right through each other. So how would I represent this with a vector field? And the big idea, this is a really clever idea, the big idea is to recognize that while we have this formula down here, right, we saw this on the previous page, if you have a vector field representing velocity and you want to know how much quantity per unit time of fluid is passing through? Well, this formula on the right tells you how to compute what's on the left. Right? So we've thought of this formula in some sense as going this way to the left. Let me try to draw that better. This formula goes this way. We know what's on the right. We use it to compute what's on the left. We're just going to turn that around. The idea here is that while I have no idea what to use for my vector field, I can empirically say that for any area, whatever little piece of area I'm talking about, I can set that area up in space. I can measure how the photons are flowing through it. And whatever that answer ends up being, whatever this quantity per unit time of photons is, the vector field representing the fluid flow needs to be something that will make this equation work. Right, so instead of a known vector field allowing us to compute flow rates tell us what the vector field should be. So now doing this in practice is, again, I wish we had more time for this. This example that follows, super interesting, a lot of fun. This would be, oh gosh, this is one of those things that really makes me sad to not have time for. If we were to include this in the course, this would be one of my favorite things. Certainly my favorite thing we would be doing this week. But still, it remains we don't have time for it. So I'm going to put a big box around all of this and cross. Y'all are not responsible for this example, but if you're interested, give it a look. If you have any questions, come talk to me. This is a fun example, and it's really interesting how this takes what seems like an intractable problem and turns it into a fundamentally simple answer. So, at your leisure. Okay, moving along. Let's see here. This will be our last thing right here. Let's see, by the way, how are we on time? Yeah, okay. This will be our last thing. Back to thinking of the vector field as representing velocity. I want to think about a two-dimensional flow of water. I'm going to be thinking about like a river, like a little creek or something. Right? I think we all probably have some experience with the following. If you're watching a creek flow, and if you take a dead leaf that you picked up off the ground and toss it into the river, it lands and then it flows downstream. Of course it does. Right? Let me say it a little bit differently, though. The leaf does exactly what the water tells it to do. The velocity that the leaf follows is exactly the velocity of the water. It's literally just floating on top of the water. If the water moves, the leaf moves too, of course. Is that right? Physical experience? Does that kind of ring satisfying, I hope? So that's all this says right here. This equation that I'm going to start with, if I can get this to zoom, here we go. This right here just says that if you were to drop the leaf into the water and you want to know what is the corresponding velocity of that leaf, well, the velocity of the leaf is whatever the velocity of the water is. Specifically, the velocity of the water at the location where the leaf is. So again, this is just, again, anytime you've looked at a floating leaf floating down the river, this is just describing that scenario. I think it's very believable. And then you recall that, get this thing to minimize, there we go. Recall that, of course, in this scenario, we're assuming that the vector field represents the velocity of the fluid, velocity of the water, and so we get this nice little punchline that here is what we call a system of differential equations that will describe how to find the path of the leaf, called a flow line. So any function that satisfies this equation is called a flow line. Any parametric curve, I should say, that satisfies this equation is a flow line. An easy example of this is the following. We look at this vector field real quick here. Here's a vector field. This is the sort of rotating fluid that we saw on the very first page of this section. So it's kind of going around like so, right? If you were to take this vector field, write the corresponding system of differential equations, solve and find paths that satisfy this resulting system of differential equations, what you would find is that this path right here is one of those solutions. And I think this is pretty believable. I mean, this is our stirred pot. This is a vector field that has the water kind of doing like this. And when you drop a bay leaf into that stirred pot, it goes in a circle. And you see that this parametric circle is one of our solutions. So that's all a flow line is, and pretty intuitive, and super quick observation. Please don't make a choice between force fields like gravity and electricity, and fluid flow fields like stirred pots and stuff like that, photons, etc. Both of these are going to be really important in the course, so please do make sure to be comfortable with both of those examples. See y'all later. Have a good one. See you on Wednesday.